welcome to our 5th season of the WILDLABS Virtual Meetup series. This season we are so excited to be focusing on ecoacoustics in our season titled Listen to the Future. Our virtual meetup season this year is part of a bigger project. We're embarking on a big bioacoustics horizon scan in which we're going to go through a formal horizon scan process to explore where investment and innovation is needed to move the bioacoustics field forward. So to support us in this project, we've been joined by an expert advisory committee who will be speaking at each of these events and who have been amazing so far at helping shape these events and shape the frame of the full horizon scan, and we're really thankful for their support and involvement in this project. And we'd also like to thank the Betty and Gordon and Betty Moore Foundation for their support as well. Now, when I say horizon scan, there's a formal process that we're going to go through, and some of you might be familiar with it. You might have been a part of our movement ecology horizon scan, but really we're in we've done a literature review. We're in this second phase of this horizon scan process, in which we're getting community input into the big list of ideas that go into the horizon scan. We're scanning for ideas and ideas about where the future of the field is going in terms of hardware innovations, data analysis and AI, data platforms, sharing and archiving, and policy integration and scientific impact. And so in this part of the project, we're holding these big community conversations to have this discussion about bioacoustics with all of you. And we're hoping that it will bring up ideas, create connections, create potential collaborations to help move the field forward. And we're hoping that some of the ideas that come through and that might be surfaced through these conversations will be able to feed into this horizon scan. So we would really encourage you, if you have ideas about where the future should be, where the field's going or where it needs to be going, to get involved in these conversations over the next 4 weeks, but also to submit ideas into the horizon scan as well. And I think, I can't see the chat right now, but I suspect Alex, Tyler, or Vanessa will have dropped in a link to where you can add your ideas into the horizon scan solicitation. And so what we'll basically do, we'll get a big list of ideas of where the future of the field is, and then we'll convene a big group of experts in our movement ecology series. I think we convened 40 to 50 experts, and basically we'll support the experts to go through a prioritization exercise to see what the priorities are from the community, and we'll come out with a prioritized list of 30, I would guess, 30 priorities about where the field is going. And what we're hoping it will do is give a collective articulation to where investment might be needed on the short, medium, and long-term horizons. And in our previous horizon scan, we did them on 5, 10, 20-year horizons. And I think one of the things that was really useful to frame the horizon scan conversation and to frame this conversation that we're going to go into today is to just think about these different horizons we can be thinking about. There's the short-term horizon where we kind of know where innovation is, what innovation is possible, and we just need some brute force, like we just need money or time or like resource to get there, but we know where the steps are. And then when you think along a longer-term horizon, this more blue sky thinking, there are ideas that could be amazing and really impactful for conservation or really change the trajectory of the bioacoustics field, but we don't quite know how to get there. And we really want to be exploring both, and not too focused on the short term, but also not too focused on like completely like unrealistic blue sky, no idea how to get there. So we're hoping to cover a mix of those sort of ideas and be thinking through them in these conversations and through our horizon scan. So, like I said, this is the first in a series of 4 virtual meetup events, which are really our open conversation with the sector. And so This first one, we're going to be talking about hardware innovation. Next week, we'll be covering data networks and platforms. The following week, we'll be covering data analysis and AI. And then in our final week, we'll be talking about policy integration and scientific impact. So really grounding our the innovations in what it means for the field and how it can have impact. And so today, I'm really so pleased to be able to introduce our 4 speakers, Laurel, Martin, Mona, and Carlos, and welcome them into the virtual meetup space. And so after each speaker, they're going to have a little bit of time to talk. They're going to have time, and we'll have a little bit of time for questions, but then we'll have a big conversation with all 4 speakers about hardware innovation and with all of you. So enough from me. I'm going to hand it over to our first speaker, Laurel, who's going to introduce the topic and give us the lay of the land of where we're at with hardware innovation for ecoacoustics.
Hello, it's a pleasure to be here with you today. Give me a moment to get a PowerPoint up for you here. And so my role today is not to give a talk on a specific topic. Well, it is on a specific topic, but not a deep dive on any one piece of this, but rather to frame the broad question and the reason we're here. So we are part of the Bioacoustics Horizon Scan, and we're focused specifically today on hardware innovations. And as I was thinking about this, there are lots of exciting things that connect to hardware, and I kept having to bring it back to hardware. So it's fun to start here, and then I look forward to seeing it branch out from here. So as a moment of historical context, if you were to look around at the world of sound recording in 1935, it looks something like this. So this is some of the first sound recordings that were made in North America. This is Peter Paul Kellogg. This is his amplifier. You haul it around in a wagon and then a large van, recording on wax cylinders. And so this is less than 100 years ago. It's pretty awesome to think where we've come within the human lifetime. So to jump forward nearly a century, these are some of the more recent devices, but even as early as the 2000, 2010, a lot of the equipment that was being deployed was being custom made by the people who were doing the recording. So this is the Elephant Listening Project. These are marine autonomous recorders. And a lot of that remains true. The people who work in bioacoustics are often sitting at the interface between biology and engineering, using the equipment, but also pushing the horizons of that equipment. Jumping forward even more, this is now overlapping work that I've done. We wanted to record the sound of Panamanian rainforests at different heights in the forest. And at the time, it took like 50 pounds of equipment or 22 kilos on a rope. And you only break that rope once before you realize we still need some hardware innovations. It takes a surprisingly long time for something to come down 24 meters and hit the ground. But if you look in the last few years, there's been just an explosion of the availability of terrestrial hardware. We have to update this slide all the time. I'm sure it's out of date. I'm sure some of you are looking at it thinking, the thing I use, the thing I make isn't on there, but you can look at this just to see the diversity of options, of price ranges, of advantages. Are you running as long as you can? Are you as sensitive as possible? All of a sudden, there's a ton of acoustic, especially terrestrial hardware available. So to think of this in the framework of the Horizon Scan, I'm going to give just a few of the high-level things that I think fall into each of these bins to sort of start our thinking and the conversation. I'm hoping that our speakers today will do a deep dive into some of them, and then I look forward to hearing from the audience more details about each of these and what you see in these bins. And 2 of the bins I think will be prominent is what is the role of hardware in enabling us to go beyond presence or presence absence. So are there ways that we can use hardware innovation to help us understand density, species presence, localization, things like that? And also on-device detection. The vast majority of the recording that we do now is stored on a device, on SD cards for later download and processing. And are there ways that hardware can help us move toward either more rapid data acquisition or more pre-processing on the unit to make it easier and faster for people to convert sound into actionable information? So some of the things that I think sit on that first horizon, I already mentioned the availability of terrestrial recording units, or at least the affordability, depending on where you are in the custom situation, and even during COVID, the availability of electronic components. The availability piece is still a little soft, but we are light years away from where we were even in the early 2000s. And in parallel, we're seeing decreasing size and cost of marine recording units, digital storage, larger storage media, more robust scheduling options that allow much longer recording durations, and decreased electronic noise floor that increases the detection radius. But Jan, probably all of us here are somewhat familiar with these things that are improving our lives right now. So where are we going? Some of the things that I think sit on that second horizon include things like multi-element microphones. And so if you take multiple microphones recording simultaneously, you can decompose original recordings into sources that are in different locations, which can greatly facilitate some of the automated identification approaches. Kind of a boring technical one, but also super important, is improved microphone characterization so that across different types of equipment throughout the lifetime of a microphone, we're using something like a tone sweep to enable us to calibrate across projects, across time, to really be able to pool data and make broader scale inferences. Things like contact microphones and lasers for vibrational signals, we're just discovering as the technology gets better, we're getting a deeper and deeper look into soil invertebrates, invertebrates that live on plants, agricultural applications of detecting insect vibrations and separating out disease-carrying pests and potentially beneficial insects. Things like acoustic cameras that use microphones combined with video feed to provide information either on how many animals or what species of animal is producing sound. So for fish, this can be really valuable because you can be snorkeling and hear fish, but who knows which fish is producing that sound. And here's an example of that. This is a pond full of wood frogs up in New Hampshire. So the colored dot lands on the sound source. This is a ring of 48 microphones surrounding a video camera, and it's decomposing where the sound occurs, along with a measure of amplitude. And so you can imagine getting much better information about how many frogs are calling in this, as well as the cool social dynamics. Enough frogs. Onboard detection of focal signals. So this is using the instrument itself to find signals, and that enables both real-time monitoring, where you can be transmitting that information, whether that's rare and endangered species, potential human-wildlife conflict species, chainsaws, gunshots, information of immediate conservation relevance, or just simplifying the analysis pipeline so that people aren't going out and coming back with SD cards with 300 gigabytes of data, but instead retrieving a curated subset of the signals in the environment. But there's quite a bit of work to be done to make this reliable and well validated, as well as the rise of distributed acoustic sensing. And if this isn't a familiar concept, one of our speakers today is going to do a deep dive, so I will leave it for that, but super exciting innovation, especially on the marine side. And then the fun speculatory third horizon. So things like, if we see qualitative changes in battery life or the ability to transmit signals, what does that, how does that shape how we can deploy equipment? Affordable equipment with highly accurate clocks. Some of this is out there, but the ability to deploy lots of equipment that can do localization. Drone-assisted placement or data collection, a little bit sci-fi, but for things like gliders and marine environments, already an important part of how we do work. Improved animal-borne recorders or acoustic tags that can provide information about cue rate, types of vocalizations produced by different individuals, dial patterns and vocalization and individual activity, which are really important features of calibrating and benchmarking some of the density estimates, as well as improved hardware supporting DAS, so miniaturization and cost reduction. So with that, I will turn it to either to discussion and questions or straight to our speakers for a deep dive on these topics.
I think you got a unanimous, like, that was a rip-roaring tour of the current state of the field and what's coming up, and you got a unanimous like gasp of excitement in the chat.
Oh, awesome.
I don't think there were specific questions. I think that actually set us up perfectly to dive deep and then come back for a general discussion. But thank you so much, Laura. That was perfect. I'm going to hand over to Martin now. And Martin, while I'll let you get set up with your share screen and making sure click the right button. But while you do that, I'm just going to do a little intro for you. So Dr. Martin Landrø is a professor and leads the Centre for Geophysical Forecasting at the Norwegian University of Science and Technology. He's a member of the European Association of Geoscientists and Engineers and the Society of Exploration Geophysicists, the Norwegian Academy of Technological Scientists, and the Royal Norwegian Society of Sciences and Letters. That is a mouthful. You're a part of everything. But I think the main point today is that you're leading some incredible work on DAS and are going to talk to us about some of like the true you're at the forefront of pushing the boundaries of what we can do with acoustics and sensing the marine environment. So I think you're going to lay some groundwork for us for where innovation is going in that space. So Martin, I'm going to hand it over to you. Take it away.
Thank you very much. Let me see. This slide shows you a map of from Svalbard, north of Norway, and it's this is our main lab, I would say. We are using 2 fiber optic cables that were deployed in 2015, entirely for the purpose of telecommunication between Ny-Ålesund, which is a small research facility. It's mostly researchers who live there, 40-50 people live up there, to the bigger city called Longyearbyen down here. The distance is 256 kilometers. And in 2015, as I said, the government in Norway decided to spend a lot of money to connect these 2 cities via 2 fiber cables. And we are allowed to use these fibers for also for sensing. And we are used so since 2020 approximately. So this is our main lab. So what you see is the 2 fibers, approximately 250, 260 kilometers long. They are trenched into the seabed, approximately 1 meter below seabed. There are 2 because they wanted to have like a spare one. The depth profile is shown on the bottom. So you see for the blue and the black cable. So it's it goes down to almost 400 meters, but it can be shallow, like 60, 70 meters also. So in this area, we have a lot of whale activity, and that was our main focus actually when we went up there in 2020 to do recordings. This is just the same figure, but seen from a map view. So Ny-Ålesund, this small city, is here, and the cable is diving into the water here, and goes fairly deep in the beginning, and then it climbs onto the shelf here, west of the island called Forlandet, and then it goes south, and then into the fjord called the Ice Fjord, which is shown here. So that's the track of our laboratory. So the nice thing about this is that we can continuously monitor 256 kilometers by using the distributed acoustic sensing. So for those who are not familiar, this is a slide that summarizes the principles. What you need to do a DAS recording is this interrogator, which essentially is a laser source, and a big computer to store all the data. We store approximately 4 to 7 terabytes per day. So it's a lot of data. It's an enormous amount of data. The principle is that you send in a beam, a light beam, into the fiber. And if you have an acoustic signal that is close enough to the fiber, then the fiber will stretch a bit. This stretching is typically of the order of nanometers. It's very small, but since you are using light, we can use cross-correlation techniques, as it's hinted up on the upper right here, to find out where this sound hit the fiber, and also the strength, how strong was this sound. So that is what we are using to monitor a long distance. So we measure typically every 10 meters, every 5 meters or so. We can design that in the interrogator. So we can also decide in the interrogator which frequencies we want to listen to. For long fibers like this, we are currently, the technology has a maximum, I would say, of 1 kilohertz typically. So that's the principle. So this is an early work was published by Lea before 2022. So what we tested first was, could we see ships that cross the fiber? So to the upper left here, you see a ship that is the AIS position or the GPS position of the ship is the red line. So that's the truth. The black line here is the fiber, and the numbers in black is the distance from the interrogator. So it's 86 kilometers away from the interrogator. And the white dots shows our estimate of the ship based on the fiber only. So this means that we are able to reconstruct the track of this ship within, I would say, 1 kilometer before the ship crosses the fiber, and also 1 kilometer after. We can also see, as you see on the lower left figures here, that we can measure the Doppler effect when the ship is moving towards the fiber and away from it, like an ambulance that you hear in the street. The sound is changing a bit. The Doppler effect is very minor here. It's 0.1 hertz or something, but despite some noise, as you see here, we can still see it. To the right, we come to the whale listening. So to the upper right, we see blue whales at 36, 37 kilometers away from the interrogator. And they are beautiful hyperbolas that you see here. And at 39 kilometers, you see another whale, probably a fin whale, vocalizing at approximately the same time. The horizontal scale here is 90 seconds, 1.5 minutes. So if I'm lucky now, I can play. Oh. So what we hear here is the reconstructed sound from the blue whale. The strongest signal was at the beginning, up and down shape, and we have multiplied the frequency by a factor of approximately 3 to make it more hearable for the human ear. So we are able to reconstruct the sounding based on this fiber optic cable that is buried below the seabed, and reconstruct the sound track of whales. We can even use the signal from the blue whale and use again cross-correlation techniques to make an image. So this is a typical what a geophysicist like me like to do. You make images of the subsurface. So what you see here is that you get first at the fiber, the red line here is the direct arrival from the blue whale. The orange line is the first reflection from the seabed. That has been reflected from a layer below the seabed. So if you see this cartoon to the upper left here, you see how that event has been going down maybe 100, 200 meters below seabed. So that's the second reflection, and then you get multiples and so on. So in this way, we can construct, we think, almost like construct an image of the subsurface using the blue whale as a seismic source. And the interesting thing for me here is that the blue whale has sufficient energy and sufficient voice to see at least 100 meters, maybe 200 meters below seabed. So the blue whale has the ability to discriminate between, for instance, sedimentary rocks at the seabed and basaltic rocks or bedrocks, if you will. Bit more technical here. What we like to do is to track the whales. And we know the position of the fiber. We know the depth of the fiber, so X and Y is is unknown. These are the position of the whale, X and Y. Z is the depth of the whale, and X and Y here are known. So this is very similar to when we determine the position of an earthquake. It's the same thing. We have a zone or source, and then we use techniques like this, inversion techniques, to determine the position. So in this way, we take the data and we are able to find out where the whale is. So this is done in an automatic way. And in the case when the whale stops to vocalize, and that is one example that we show here, then the uncertainty ellipsis that we compute increases. And then we see that we are just doing extrapolation, which is wrong. So you see this straight line here, this stars. But then the whale actually appears to the left in the figure, but it's inside the ellipsis of uncertainty, so we find it again. So then we continue to track it. So in this way, we are able to follow the whale when if it's not stopping to vocalize for too long period. Yeah, these are just examples of how it looks like on the dust data for various. Here we have 2 fiber optic cables, inner cable and outer cable. So we see here we see 3 fin whales vocalizing at the same time. This is the sound profile again, and we can identify where they are. So by looking at this in real time, like we see here, the red dots that you see are when a whale is close to the fiber. So there, for instance, and then you see the signal at both fibers, but at the delayed time of the other fiber. You see one there. So in this way, we were able to record and track the positions of up to 8 whales. This was fin whales at the same time for a period of 5 hours. So that's where we are today. That's what we think is possible. So the next step is then to do this on a yearly, to extend this in a more massive type of analysis. It's an advantage to have 2 fibers as we have here, because it's easier to do the inversion to find the exact position, to avoid what we call the mirror problem. So this is a summary of our analysis so far. Here we have baptized each whale with from A to H here. So we see that, for instance, whale B started approximately here and slowly moved along this path and going almost westerly. And then we kind of lost contact with this whale after 2 to 3 hours. The color bar at the top here is the time in hours. So it's from 0 to 5 hours. Whale D here we see goes south, close to the fiber, makes a turn, and goes back, and so on. Some of the whales seems to be stationary for more than 4 or 5 hours, but vocalizing now and then. The limitations here are, we would say, it's shown by this dashed white line. So it varies with the distance from the interrogator. So when it's come like 100 kilometers away, we lose accuracy. But typically, you can say that maybe 5-10 kilometers from each side, we are able to find these whales. And we can estimate the direction and the speed and so on. When we have the track, we can actually analyze a lot of things. So I think that's it.
I think Bevis captured kind of the feeling in the chat by saying, like, wow, this is incredible research, and they've never seen existing infrastructure used so effectively and creatively. So I think that captures the general mood of the chat and just excitement and interest in what you're doing. I'm going to throw to, I think I'm going to throw to Ord first. Is that right? Yes. Ord, do you want to jump in and ask your question? You jumped in first.
Yeah, sure. Thanks a lot for this wonderful talk. So I'm wondering about the timeline between the data collection and the data analysis, and if you're interested in knowing the new real-time location of the wave. So, yeah.
Yeah, so presently, as you saw on when I showed the plot where you see these events along the fiber, you get an impression of where the whale is, but not exactly. So to find that exact positions, we need to run like a grid search or an inversion, mathematical inversion. And that we cannot do online today. That requires high performance computers, but we're working on that. And the key word here is probably edge computing, that you within close to the interrogator, you analyze the data and try to find out as quickly as possible where the whale is. But we are not at that stage yet, I would say. But that's definitely a goal, and that we want to pursue. So it's a lot of challenges there.
Yeah, amazing. Thanks. Very interesting.
Carlos, do you want to ask your question?
Hi, yeah, sure. Hi, Martin. Thanks. I was just wondering whether this has been used in other contexts within sort of terrestrial environment, and whether there's sort of amplitude and frequency constraints that would enable that, or whether it's quite limited to sort of the marine.
Yeah.
Very
So far, it's possible to, as I said, it's possible to go up to 10 kilohertz or even 100 kilohertz, but then you have to limit the length of the interrogating length. So typically, if you have 10 kilometers of fiber, then you can probably go up to 10 kilohertz. So you can, for instance, listen to humpback whales and things like that. But presently, this is also a challenge, I would say, to have high frequencies and long distances at the same time. We are not that yet. We are not there yet. But it's an enormous challenge, of course, because you want a lot of data at the same time. So for terrestrial use, we have tested it close to railway and tried to test if we can see, for instance, a moose that gets close to the railway track to give a warning. It's much easier to detect persons. A walking man is much easier than a big moose, Norwegian moose. It turns out, so that's more challenging, I would say. But there are, of course, a lot of terrestrial uses that are easier in a way than if you go offshore. It's because then you can just put out your fiber for a short time or period, and we have done a lot of tests like that. So that's yeah.
Pete, it sounds like you wanted to jump into that conversation.
Just had a question.
Or are you jumping the queue? Are you jumping the queue? All right, you can jump the queue. Go on.
Sorry, I didn't intend to.
No, you're fine.
Actually, it's a direct question about the terrestrial application, because I know that the sheathing on fiber that's being used for underwater runs and the acoustic impedance between the ocean water to the sheathing to the fiber itself, that's a much more direct continuum in the same order of magnitude for acoustic impedance. But for terrestrial, are you actually picking up more of surface wave stuff insofar as whatever the medium is that you're connected through through some sort of acoustic grounding? Like if this is on a telephone pole or running underground, are you actually getting more transmission of sound through solids rather than through air? Because I'd imagine that the air to sheathing impedance is significantly higher.
Yeah.
Just wondering.
That's correct. So I fully agree with what you said. It's for terrestrial use, it's the surface waves we are picking up. So if you have footprints like animals in contact with the earth, then you get that fairly strong signal. But only acoustic signal through air is a bit more challenging, but it's not impossible. But it's weaker, as you said.
Wonderful.
Thank you very much.
That was a clarification of our facilitation. If Pete, you did exactly the correct thing. If you want to add something to the live conversation, put your hand up and I'll call you. But if you have a question that's like on a different track, put it in the chat and I'll call on you there. One last question, I think, maybe two. Xavier, did your question get answered in the talk?
So I think it was, yeah. So that and Leah replied also about the frequency signal. So I think
you're good. Okay. Aoife, did I get your name correctly first? But I think you have our final question.
Yes, you nailed it.
Yes.
Thank you. Hi, Martin. That was a really cool talk. I'm actually a geophysicist by background, so I've read some of your papers on 4D seismic. So really enjoying this. I was wondering, you know, whales are not always vocal creating strain waves anyway. Are those just way too low amplitude to be able to pick up the strain waves from their movement?
Can you repeat that? What was the weak amplitude you say?
Sorry, I think my network connection is not great, but I was wondering whether it would be possible to detect whales when they're not vocalizing from the strain waves that are coming from them moving through the water.
I would hope so, but presently we are not. We are far from that, I think. We are dependent on whales to vocalize, and more subtle signals, like you mentioned now, I think we have to be, that's in the future, I would say, because there are background noise and there are challenges here that we, even to detect ships that you might think we make a lot of noise, it's actually often difficult, especially if you're far away from the interrogator. So it's not that, it doesn't solve all the problems, certainly not. So you need a certain signal to noise ratio to detect. But maybe in the future, we become more sensitive. So the current range is, as I said, 100, 120 kilometers, but there are developments in this interrogator technology that makes this possible maybe in a few years to have covered 200 kilometers and so
on. Okay, cool.
Thank you very much.
Okay, you've got a few more questions coming in from Chris and Carly about scalability and concerns from the Navy, but I'm going to wrap the discussion up here. And Martin, you can pop into the chat and pick up those questions there. Mm-hmm. And now I'm going to throw it over to Mona. And Mona, while you're getting set up with your talk and screen share, let me just do a little introduction. Mona Doss is the Vice President Business Development at Wildlife Acoustics, one of the leading providers of bioacoustic monitoring and recording technologies for scientists, researchers, and government agencies worldwide. So I think a lot of you are very familiar with Wildlife Acoustics, and we think it's really important to have some of the actual commercial hardware developers in these conversations, same for analytics, the analytics conversations. So Wildlife Acoustics are used by so many ecologists and conservationists that having you guys here to share your insights and what you see as the innovation needs on the hardware side of bioacoustics is super important. So we're so glad that you've been able to join us today. So thank you very much, and take it away.
Thank you. Well, hello, WildLabs community. I recognize a lot of names in the participant list, and I'm so glad that you're able to join us this morning. Thanks to WildLabs, Colorado State University, and the Moore Foundation for the opportunity to participate today. As mentioned, I'm Mona Doss. I'm VP of Business Development from Wildlife Acoustics. I've been with the company about 13 years, and I've had the privilege of seeing hardware from the bioacoustics market expand a lot during that time, and thanks to all your hard research and work. Now, when thinking about technology hardware innovations, and it's going to be interesting because I think I've got a lot of content in here which mirrors some of the points that Laurel was making in her first presentation. And it's nice to see, we didn't see each other's presentations, so it's nice to see some complementary thought thinking here. But first, I want to take you a little bit back down memory lane in terms of the history of our technology and innovation in this market. Wildlife Acoustics has been continuously evolving and improving our technology since our first prototype of the Song Sleuth bird recorder and ID appliance back in 2003. You probably have never even heard about this product. But it was, now everyone's got, you know, the Cornell's Merlin app on their phone. But back then, to have an appliance that would take a sound and give you species ID for most common birds of North America was pretty innovative. Now, commercially, that product was a flop. If you were a wannabe birder, you couldn't afford the $300 price tag. And if you were an avid birder, you didn't need it. But that first song sleuth appliance got us on the track of innovation in terms of bioacoustics. And just a few years later, in 2007, we were the first company to produce a commercially available wildlife audio recorder designed specifically for field work. So biologists now had an all-in-one weatherproof solution to monitor wildlife and soundscapes passively. Now, previously, ARUs required a do-it-yourself sourcing and assembly, or some had limitations on being commercially available. At the time, the Songmeter SM1 was a game changer, presenting a convenient, cost-effective tool for monitoring birds and frogs and other audible wildlife. Of course, we've come a long way since then with many iterations of our Songmeter recorders, but that SM1 marked a significant milestone in the industry's evolution, with bioacoustics gaining popularity because it allowed scientists to gather data at scale affordably. Now, in 2009, we introduced our first Songmeter SM2 BAT recorder. It was the first commercial weatherproof static bat detector. A year later, we introduced the first handheld bat detector that had an integrated spectrogram. In 2014, we produced the first bat detector that integrated a smartphone app with our Ecometer Touch product, and that refined that a couple of years later with our Ecometer Touch 2. In 2019, we were the first to produce the static ARU that could be programmed and controlled on the phone with a mobile app with our Songmeter Mini and Micro families. And in 2022, we produced the first commercially available bat detector with real-time onboard analysis that triggers an alarm for a wind farm to curtail in the presence of bats with our smart system. Now, what drives that technology development at Wildlife Acoustics? You know, first, we want to make sure we're providing practical, reliable, and affordable tools for biologists. Our product team spends a lot of time and effort trying to push the boundaries of possibility. You know, if we build it, will they use it? But besides that, we also listen to the bioacoustics community. Our last survey had over 1,200 complete respondents, and I'd like to share with you a little bit about what you all said. For the bat biologist community, when asked how many nights they deployed, 40% responded with 5 to 15 nights, 40% had greater than 15 nights, and everyone else recorded less than 5 nights. And of those respondents, 30% also said they're deploying bat detectors that could record also birds, frogs, and other sounds in the acoustic audible range. For folks doing recordings in the audible range, 55% said, yeah, we're going to record 2 weeks or less, and 45% said recording greater than 2 weeks. When asked what they were looking for out of recorders, there was a lot of feedback there. They want built-in GPS, alternate to windscreens, multi-channel recordings, larger battery compartments for longer deployments, lighter, more portable devices. Those seem to be quite on the opposite side of the spectrum there. Better weatherproofing, real-time recording capabilities, remote data download. And if you look at this, it almost seemed like, in the rest of the surveys that I haven't shared with you, the market's kind of split in two. Half our customer base wants longer term, more battery life. The other half wants, oh, please make it smaller and more affordable. And that's what we spent our time doing. So based on that data, in 2024, we focused on increasing battery capacity with the next generation of our Mini and Micro products. We doubled the battery capacity of the Mini 2 alkaline model and improved the battery capacity of the Songmeter Micro 2 by 30%. All significantly growing without significantly growing the footprint and the size of those song meters. So we still kept it small, but we gave you more deployment time with better battery capacity. We also flattened the frequency response of the Micro with the Micro 2 for folks doing soundscape and acoustic indices research based on some other feedback we got. For improved weatherproofing, we re-engineered the latch enclosure from the previous models. But besides that, we also invested heavily in environmental testing. Now, we always have done environmental testing, but our customers are really pushing the envelope in terms of deploying in the tropics, the desert, the Arctic. And you need one solution that can withstand all those environmental challenges with not losing 30% of your data. So to ensure our second generation Mini and Micro families perform reliably in all weather, besides that latch improvement, we repeatedly subjected them to extreme humidity and environmental testing in our environmental test chamber, where we tested the recorders to make sure they could withstand sustained temperatures at 55 degrees C all the way down to minus 20 degrees C, and then we cycled between those extremes. We also submerged them in our immersion tank, 1 meter of water for 30 minutes to certify the weather resistance of the enclosure if all the microphone holes were plugged up. Now, since founding in 2003, Wildlife Acoustics has always been about developing bioacoustics tools that propel scientific discovery and conservation. And thinking back from where we started with our original Song Meter 1 days, we're so glad the market has expanded in the years since, and bioacoustics is becoming even more accessible for critical research. Now more than ever, the biologists and scientists need access to acoustic recorders that they can deploy at scale reliably. And our commitment to that accessibility and affordability of bioacoustics is unwavering, which is why you all are getting a sneak peek. No one else knows about this worldwide yet. But we've decided to drop the price of our Song Meter Micro 2 from $249 to $149. All the website changes and formal communication will be going out next week. But this is primarily due to operational efficiencies and improvements in our supply chain that's allowed us to make this price point lower, and we're passing that savings on to you. So, as bioacoustics rose, because it's become more affordable and approachable, and in a world where costs are going up, this is a unique opportunity to provide a price reduction on the Micro 2 and support the community. Now, besides lowering the price, the other way we're trying to help the bioacoustics community is get the most out of the budget by improving recording quality and microphone performance. That's something Laurel talked about earlier in one of her presentation slides. Last year, Wildlife Acoustics invested heavily in hundreds of thousands of dollars, in fact, on a sound testing lab equipment. It's an anechoic chamber with Brule and Kerr calibration microphones. By having this sound lab on site, it allows us, with our engineers, to experiment and iterate in real time during the development and early pre-production stages to basically design high fidelity systems that actually accurately capture the sound. The result, you get cleaner recordings. Why does this matter? So this sound lab investment translates to improved microphone recording recorder performance, which increases your sphere of detection. So let's say you hear a sound at 25 meters without getting into a lot of math. If I can improve that system signal to noise ratio by 6 dB, assuming there's no single attenuation of absorption or reflections in the environment, then in theory, I could hear that sound by that 6 dB improvement 50 meters away, which means if you're defining a project, you need less recorders than otherwise planned. Or if you're buying a budget, you can buy more recorders and cover more airspace. So it's not just about getting the manufacturing costs down, but it's also about improving the technology with these kinds of innovations of the Sound Lab so that you can cover more soundscape with the same recorder that otherwise you might not have. Now that was great for those that wanted more affordable, more battery, but lightweight. Looking at those respondents from the survey, they also wanted long-term solar panels, more batteries on that side of the spectrum. And again, this is a sneak peek. No one else in the world knows this yet, but in October, we are going to be introducing our power kit. It has an integrated solar panel with a battery pack and the necessary accessories and cables to support external powering of the SM3 and Song Meter SM4 family of recorders. What's compelling here is that price point. Before, customers had to source the solar panel, buy the battery kit, get the cable from us. That was a headache. And then when you started adding the costs, it was a lot higher than $199 USD, which is what we're going to be introducing that adds. So taking the feedback from that survey, we've tried to at least address longer term deployments, more portability, and improved weatherproofness. But what's next? Well, we're always developing. I can't go into too many details, but just think back on some of those survey questions and feature requests. In general, customers are asking for remote networking, edge computing, improved classification methods. And when asked to do this talk, I was asked to also share my thoughts on what we could do to solve with brute force at this point to expand innovation in bioacoustics, and where is investment and tolerance required for innovation. The biggest challenge is how to deliver all this in a commercially viable way that is affordable to the bioacoustics community. You might not know this, but about 10 years ago, we introduced a product called SongStream. This provided remote access and download of data over a cellular network for our Songmeter SM2 family. Great idea at the time, but it was too expensive for the bioacoustics community, not only with the hardware, but with the monthly data subscription fees. Now, a lot has changed in 10 years. We were kind of ahead of the game at that point, I think. Cellular innovation's gotten a lot better. Everything is connected. But looking back at all the innovation we've done, it's been possible not only because of the inspiration of our product team, but also by advancements in technology. We're leveraging advancements in the consumer market to drive down costs in the bioacoustic sector. For instance, if you can program a recorder with your phone, cell phone, which we all now have, then you don't need to add an expensive LCD display or a keypad to a recorder, which is how the Mini and the Micro families were able to provide a more affordable solution to the market. It's this cycle of innovation that drives what we can do. So innovation in academic research from the technology side drives innovation in the consumer side that we leverage to offer affordable solutions for bioacoustics. And that enables your research on the environmental side. So basically, as consumer technology advances in all the areas that the survey respondents were asking about, you'll continue to see innovative products from Wildlife Acoustics. And that's it. Thank you, everyone. Look forward to the questions.
Thank you so much. Vanessa, I'm actually going to throw, oh, Vanessa's not here. I'm not going to throw to Vanessa. Vanessa, are you here? Surprise.
Yeah, I'm here.
I'm going to throw to you for your question first.
Hi, thank you, Seth. And great presentation, Mona. I was wondering, looking at the cycle of accelerated innovation that you show in your last slide, how what specific actions or partnership are needed to further accelerate innovation and strengthen this commercial and academics partnership in this field?
Yeah, I think it starts with innovation on the technology side of things. Now that could be by private companies, you know, because of Apple, we now all have smartphones, right? Or by technology innovation in the academic sector in terms of creating new methodologies to lower the price point of how to do something. Now, just because something can be done, like you saw with our SongStream product of 10 years ago, yeah, we can transfer data. We did that 10 years ago, but it wasn't at a level of affordability. So it's folks like Wildlife Acoustics and other innovators who look at the market and see what is available in the consumer space that we can basically cheat off of to drive the costs down so we can give you tools to allow you to be able to do the research you want to do in a way that's affordable. So I think it's really a combination of academic and the high-tech industry and what they think of that we can then say, ooh, let's steal that and help our customers here.
I think one of the, or do you want to jump in?
Yeah, can I ask a question?
Wait, Alex, I wasn't throwing to you.
Yeah.
I'll throw you in a
sure.
second.
Sure, unless you had something to say before I jump in.
No, go for it.
Okay. Hi, Mona, really nice talk. Super exciting to actually go down memory lane and see the evolution of the hardware. I have a question regarding more like the onboard edge processing analysis and how do you team engage with people that collect the data and the kind of model development? Because I guess there is kind of not a tension, but always data sharing agreement in place. A lot of researchers go in the field and collect this data. So yeah, how do you see that evolving and how do you see this kind of barrier of data sharing, model training, model transparency going forward?
Yeah, I think that when you start looking at edge computing and analysis on board, part of that equation, it's not edge computing in isolation, because if you can't offboard that data somewhere, then it's great, but you still got to go collect that data. The real challenge is that a lot of the customers are deploying in areas that don't have network connectivity. And so you know, I can give you something that could offboard something somewhere else, but unless you have, you're near a cell signal or you've got Wi-Fi, in a lot of areas in the middle of nowhere, you're talking satellite. But that's where the edge computing becomes important, because if we can get the data that you want down to really, really small bytes, then that cost equation becomes affordable and how much data you can transfer into satellite. I think it's coming. I mean, don't take that as Wildlife Acoustics is introducing edge computing, but we're doing it today on a larger scale with our smart detector product. That's the product that's doing real-time analysis, detecting bats of a certain criteria, and then triggering alarm, usually through a Wi-Fi hotspot to the turbine to pause that curtailment. So the technology is there, but that's a really expensive solution right now. That onboard computing processing, pretty expensive. So we're monitoring what's going on in terms of the microprocessor market to see how that can be leveraged in terms of how do you get that onboard computing onto a recorder in an affordable way. We're not there yet, but looking at the market, it's getting close, right? So I would say it's going to be there in the next, you know, several years, if not sooner.
Alexander, do you want to jump in? And then I'm going to move us on to the final speaker. Oh, you're muted still, Alexander.
Okay, my question is, are you going to did you consider option to incorporate localization algorithm to your system, especially a lot of about localization algorithm you considered in the first presentation today?
I'm sorry, I didn't hear the question.
Okay, question is about localization.
Oh, localization.
Can you incorporate localization algorithm or change your hardware for have option for localizations of acoustical signals, especially some algorithms were considered in the first presentation today?
Yeah, so we do offer a solution today. I didn't touch upon it for localization. That's our Songmeter SM4TS time synchronization product. So something does exist today. Certainly that platform is about, what, 8-9 years old. So again, we're always innovating. But yeah, there is a solution today. We always are looking ways to provide something better, more affordable way.
I think there's a couple more questions for you, Mona, in the chat, but thank you so much. That was super interesting, and we'll bring you back for the main discussion in a little bit. Okay, on to our final speaker, Carlos, who I'm very excited about this talk because I pinged Carlos about soil acoustics maybe 12 months ago because it came up as one of the topics in Bill Sutherland's Horizon Scan last year. And I got messages asking me, is this even a thing? And I had no idea. So I asked the person who would know, which was Carlos. And here we are, full circle. Carlos has come to talk about soil ecoacoustics. So I'm very excited. But let me just introduce you like formally. Carlos Abrams is the Director of Ecoacoustics at Baker Consultants and a Senior Lecturer at Nottingham Trent University. He works in bioacoustics and ecoacoustic survey and monitoring methods, particularly for birds, freshwater habitat, soils, and general soundscape assessment. I think we've had you on to talk about freshwater acoustics before.
And birds, yeah.
And birds. Oh my
Twice,
goodness.
I think, yeah.
Okay, all right. Well,
yeah.
third time's the charm.
The charm, maybe. This
So
will be the good talk, I think, yeah.
All right, go on.
Okay, thanks, Steph. Hi, everybody. Thanks for having me. As Steph was saying, I'm here to talk about soil acoustics, and in contrast to the two previous, this is the cheap, dirty, and very undeveloped bit of ecoacoustics, really. I've done a bit of work on soil ecoacoustics, but not alone in doing that. So I'm just going to quickly mention some of the background and other people you really want to look up for the limited amount of research that's been published on this. So Ollie Metcalf has done work in the Amazon. If you're into Amazon soils, then he's the guy. Jake Robinson, who did a bit of work on a couple of years ago in Sheffield in the UK. He's now based in Australia and has done a bit of field study there, and in the last couple of days has just brought a review out in the, if you look up Jake Robinson and soil meta review, you'll find his work that's just come out in the last couple of days in terms of looking at recording biota. Marcus Mader in Switzerland, who's really kicked the whole ecoacoustics thing off 3 years ago or so. And then there's a sort of history going back with sound recordists like Xavier Mouy and other people who've looked more at soil bioacoustics and pest management and control and detection. So a guy, Richard Mankin, who's based in Florida as well. So the recording stuff underground has gone back maybe 20 years or so, and probably longer. But a lot of that's been quite focused on small species groups, and the ecoacoustics and the broader sort of use of environmental sounds studying within soil has only really come out since about 2020 or even later than that. So it's pretty fresh, pretty new. And because of that, the methods and the hardware are in development still. So in terms of soil sounds, you can record a variety of sounds, anthrophony, geophony, whatever, so man-made sounds and natural sounds as well, but there are some biological produced sounds that you can record in soil. A lot of that is just the banging and crashing of things moving and feeding as they wriggle around in the soil, but some taxa, and beetle larvae probably especially, do produce intentional stridulation sounds, so they sound like underground crickets, and if your mic is close enough you can hear them, and hopefully this should play. It starts off quiet, but the volume increases. So it's not the most exciting of sounds maybe, but as I say, some of these coleoptera and other invertebrates, ants and some other things, produce sounds. They have stridulation features either on the legs, torso, or the mandibles that they produce sound with. And for the 3 species that have had some work done on them, they do seem to be species specific. So we can tell which beetles, as far as we know, are present if we can record their sounds well enough. Recording their sounds well enough is the tricky bit though. As well as recording those intentional sounds and taking sort of bioacoustic approach, we can also take a more ecoacoustic approach. And so some of the work that's been published by Marcus, myself, Jake, and Ollie has used acoustic indices. So some of the crowd's probably familiar with these, some may not be, but this is basically looking at rather than trying to identify characteristic sounds from animals that we know, we're just getting a measure for the diversity and complexity of the sound that's we're recording in the soil. And we can see, if you look at the coloured graphs on the right hand side, that we do get patterns in those acoustic indices during the course of the day. So what tends to happen is that the soil becomes more noisy as the day warms up during the middle of the day, and becomes more quiet again in the evening. So it's related to soil temperature, and we can see similar patterns during the course of the year. So there are seasonal as well as dial changes as well. And if we look at those acoustic indices, we can relate them to the diversity and number of soil animals that are there. So whether this graph on the left hand side is from Marcus Mader's paper back in 2022, where they took soil cores out, funneled all the invertebrates out, looked at the diversity of those and compared that to the acoustic complexity index, and you get a pretty good relationship between the two. So the more diverse the soil fauna is, the more diverse the sound is, and so we can use acoustic indices to get a handle on soil biodiversity, which is really useful because the only other 2 ways to measure soil biodiversity at the moment are to spend lots of money doing eDNA, high throughput, metabarcoding, whatever. I don't understand it, I can talk about it in broad terms, and measure stuff like that. Or we can take a spade out, dig the soil out and count the number of worms in. So at the moment there's high tech, low tech, cheap, yeah, and backbreaking or expensive and high technology, and soil acoustics fits pretty well in between those in terms of a scalable technique that's easily implementable and scalable across large areas and shouldn't cost a lot of money to do. So it's a good intermediate technology. So talking about intermediate technologies, and Mona just given us all of this stuff about brilliant wildlife acoustics kit, which has been developed over a long period of time, and the fiber optics under the sea is also really good. At the moment, we've got pretty much no idea of what an optimum system for recording soil acoustics is. We can take soil recordings using a variety of kit, but no one has really done any testing to see which system is better than others, which materials and which recordings. But basically, we need a decent recorder, and then we need a sensor that is plugged into the soil in somehow. And there are different ways to doing that. So I'm going to go backwards and start at the right-hand side of the screen here. One solution is to dig a hole, stick your recorder, whether it's a contact microphone, hydrophone, condenser mic, potentially, bury it underground, fill the hole back in, and then record sounds produced from there. That has been done by a few people. Ollie Metcalf's paper from the Amazon used this approach. The problem with that is that you disturb the soil that you're trying to record, and it's okay for long-term deployments, but if you wanted to record spatial replicates rapidly across a landscape, you can't be digging the soil up every time you want to do that. The other approach, going to the middle, is to put a sensor on the actual ground and see if you can pick up vibrations coming to the soil surface. That's been used again in some military applications, for example, to listen for tunnels on the battlefield, but in terms of recording invertebrates, maybe not that great, and you need quite a clean surface, because to get good coupling between the microphone and the soil, if you've got vegetation in the way, again, that's another issue. So the left-hand solution is the one that myself and other people in the past have used, and that is basically to stick a probe into the ground, and the probe, which is metal spike of some sort, picks up the vibrations that are produced by the invertebrates in the soil and transmits those out of the soil to a sensor that sits above the ground. And so if you can imagine taking a knitting needle or a 9-inch nail or a piece of rebar, which have all been used for this solution, stick that into the ground, clip your mic to it, then this works as a good, easy to deploy solution. And one that's been used by quite a few papers. But in terms of how that works in terms of the material and shape and size and those sorts of things, those optimum solutions haven't been suggested yet, or haven't been found out. So ourselves and others have tried different materials, different sorts of tent pegs in different types of metals. Some lab papers have also used glass probes for this, that they attack the microphone too as well. If you look at Marcus Mader's work, he prefers gold-plated copper wire. He comes from Switzerland though, so there's probably plenty of gold available in the coffers there to use that. We tend to use 2mm steel wires that go into the ground, and a little bit of testing that we've done on this shows that actually which material you use doesn't make a great deal of difference probably, and it's the size, length, and how well it couples to the soil and how well it couples to your mic are probably the more important things than actually what material it's made out of. Ourselves and others have done a little bit of testing in terms of how these waveguide, these probes should be, whether the width, the mass and the length makes a difference. Nobody knows. Nobody's published any work on that at the moment. We've got a few vague ideas on what we prefer in terms of that. And then in terms of cross-section shape, is just a narrow wire good? Or actually, if you've got more surface area, some of the original pegs we used were sort of triangular shaped tent pegs, which got really good contact with the soil in terms of the surface area, but were pretty much impossible to get into hard vineyard soils in the middle of France because the ground's too hard. So we tend to prefer narrower, thinner ones. So ourselves and other people have done a bit of testing of this, but none of this has been published at all so far. So actually, in terms of what is the optimum material, shape, size, length, and everything else for a waveguide Nobody knows. And physicists, yeah, don't like to pin their colours to the mast on this as well in terms of what's best. So nobody really knows at the moment. So the bit that goes in the ground, we can argue over what that should look like. In terms of the actual sensor bit, most of the work that's been done on this has been done with piezo contact microphones. Some people have used hydrophones in the past and buried those. Some people have used accelerometers also as well, which are quite spendy, and the information can be quite useful. It's slightly different to interpret in terms of an acoustics signal though. So I'm going to sort of park those on the side at the moment and concentrate on the other things. Because of the availability of contact microphones, most of them tend to use these circular disc type things that you can buy off eBay for about 20 pence each, or you can buy slightly better ones from people like Jesraeli French or Shirtler and spend £70 or £40, £400 or whatever, depending on your budgets. However, the same sort of material is also available as a piezo film rather than a round disc. And it's also available as a piezo cable as well. Nobody's really tested these that I know of, apart from myself and Marcus Mader. And so when you think about taking a probe object, I'm holding a pen up just because it's a long pointy thing, and trying to connect a piezo sense to the top of that, if you've got a 2mm wide, does having a round disc that's about 1 inch across and hardly contacts the wire the best option, or would a narrow thin bit of piezo film be better? Or could you actually embed some piezo cable within a metal tube that goes into the ground and potentially pick up vibrations there? Fairly similarly analogous to the fiber optic solution that Martin was talking about not long ago. So yeah, standard contact mics, they're pretty cheap, they work, and so we can get answers out of those at the moment, but are they the best solution? I don't know, nobody else does, so somebody needs to find out really. Other things that we need to think about when recording in the field are getting strong enough signal. The signals that we pick up in the ground tend to be quite short range. The soil is a very good filter, low pass filter for sounds, and sound doesn't travel very far through it. So a detection range for most invertebrates that we're trying to pick up is probably in the region of about 50 centimeters radius from the sensor. It's very short range stuff. Higher frequencies get lost super quickly as well, so it tends to be the lower frequency stuff that we do. And contact microphones, those piezo film, have very high impedance, which doesn't match very well to low impedance recorders. So you need a good recording unit with really good signal to noise ratio. So the more you spend on the recorder, the better. You probably need a preamp to boost the signal, and if you are using a contact microphone with high impedance, you need an impedance filter, otherwise you're cutting out all of the frequencies below about 250 or 500 hertz. You also want to try and protect your above ground sensor from background noise, wind vibration and contact with vegetation as well. So we take the super high-tech solution of putting a silicone bucket over the top of the microphone when we're doing field recording. And so, yeah, it's the other end of scale from a 250 kilometer fiber optic signal, I think, in terms of what we're doing, and we're still trying to work out what is the best system for that. And so to finish off, I need to plug this. We are currently working with soil scientists at Warwick University in the UK. We have about £350,000 worth of grant from UKRI, and are doing a few things with that. We are developing a prototype for a farmer-friendly soil acoustic recording device with one button and a single probe that's GPS linked. So landowners without any technical capabilities whatsoever can take recordings, standardized recordings from the field, and then upload those to our website that's on its way to do the analysis for them. As part of the work to back that up, we are developing a sound library. So we've got a couple of thousand soil recordings from farmland across the UK at the moment that we're developing machine learning and acoustic index parameters from. And also doing lots of recording of worms and other invertebrates in buckets as well, to see if we can develop ML tools to detect some of the species. So we've got sort of a range of experiments going on from very small scale mesocosms to the landscape stuff across the whole of the UK to try and get some data together to start to understand how to record soil sounds, how to interpret them once we've got them, and make that available to farmers across England, which is what our grant's for, but also conservationists and researchers and everybody else, to try and start listening to soils and making use of that for conservation and ecology research. And I'll finish there. Thank you.
That's awesome. So I guess you had a lot of comments and suggestions in the chat, so I definitely will pop you into the chat to look at them. But I guess there was one question that came up in registration. It came up a couple of times in the chat. Like, so, and I can see that you're working on it now. But how far away is just off-the-shelf tools for monitoring soil acoustics, and to get to the point where they're ready to assess soil organism abundance and diversity? How far away do you think it is?
We are doing the research. We're also doing some trial projects for some landowners in France and the UK at the moment, and so the acoustic index type of thing, we can record pretty decent field data recordings and can analyze that, and we are starting to develop an understanding of how that's related to land use, for example, and what the natural scale of acoustic indices are within soil and the amount of variation. And but at its simplest level, the more sound that is going on, the better the soil quality is, soil health is, however you want to talk about that. And I say at that level, our ambitions are fairly low. We want to be just slightly better and slightly cheaper, easier and quicker than digging worm pits, which is the current standard for assessing the soil health.
So Carlos, do you think it's like 5 years away or 10 years away, or
we're hoping to have our product out, the hardware product and the analysis website sometime, I'd say not for Christmas, maybe early in the new year, so pretty soon.
Oh, okay, really soon. Okay, cool. Interesting. Okay.
But and then the next level from that then will be interrogating that sound data in more detail and linking it expressly to, say, if we've got this acoustic index in this location, how does that relate in any way to worm numbers, for example, or other invertebrates? And so sort of crossing from an acoustic index to relate that specifically to another metric, would be also the next step on as well.
I'm sorry to wrap you up. I would happily talk about soil acoustics for the whole hour and a half if we could, but I'm going to bring the rest of the speakers back. Would you be able to stop sharing for a sec?
I can do.
And then I want to just say thank you to all of you, first off. I think that was just an incredible tour of near and further horizons of where the hardware side of eco and bioacoustics is going. So a big thank you to all of you. But I think what we heard from Laurel in particular, but throughout the talks, were some ideas about where we are right now and like where innovations are approaching on the horizon. But what do you guys see as the most significant barriers for scaling up and reaching these new frontiers on whatever horizon that you talked about or that you see as really important? I think I'm going to throw to Laurel first. We haven't heard from you for a while. What do you think the most significant barriers are, and how can we tackle them?
Yeah, I think they come in a few different flavors. There's certainly the technical barriers. One of the ones that I've come to appreciate more in the last few years is the challenge of moving equipment from place to place. So if you're trying to move equipment through customs, there are pretty substantial import taxes, delays, challenges. I'm seeing nods both from Carly and from Mona. You have to had to pry equipment out of a few different country customs before you really appreciate how hard that is. So, some of the innovations I could see coming, even in the form of open access plans that allow people to build equipment in country, so that some of the, even in the current horizon, some of the things that can be done in many places. Beyond that, hurdles, I think, continue to be battery life, connectivity. So solar panels are awesome, but a lot of the habitats where bioacoustics are most useful is under the forest canopy, and being able to really get long duration recording in those types of environments remains challenging. But those are a few that are top of mind for me.
Mona, I saw you nodding. Do you agree?
I agree with Laurel, especially if you look at the WildLabs surveys. I think the last survey you guys published, suddenly there was the line of, one of the barriers for bioacoustics is access to local suppliers. And that wasn't on your prior surveys. So, we've worked hard on trying to expand our distribution network globally to get, the equipment in the hands more locally to folks. On the technology side, I think that it really comes down to improving access to networking in the very remote sites where most of our customers are doing field work. So when you look at things like Starlink and things like that, those price points need to come down. They need to be more readily available. And then that enables, the analysis on the edge and other types of things to be done to uplink that data. So it's getting there. I mean, there's innovation going on in the networking space, but I think that is what's going to really start creating this kind of global connectivity of data sharing even, amongst projects that are just so remote right now. Not everyone has the convenience of having a cell phone signal where they're deploying the recorders.
Martin, do you agree, or what are the biggest challenges you see?
Related to distributed acoustic sensing, it's of course the cost of the interrogator. Typically an interrogator today costs $100,000, so it's costly. But given the opportunities with one interrogator, it's not that costly maybe, but it's for projects, university projects. We have 3 interrogators in my university, and we have to see it as a long-term cost, and then we use it everywhere almost. It's not a hurdle anymore to get access to fibers. That takes us some hours, but some fibers might, of course, if they are used for telecommunication, might be we need dark fibers that are not used for telecommunication at that time. So that is a hurdle that is currently being looked into. So there are systems, interrogators, that can do sensing at the same time as we are doing telecommunication in the same fiber. And then that problem is less of a problem. But those are the 2 major hurdles as I see it: cheap access to interrogators, and then to do sensing simultaneously with telecommunication.
Hey, do you want to jump in with that comment?
If nobody minds, yeah.
Yeah, for a conversation.
Pardon? Well, my perspective on the conversation is that part of the reason that the costs are high for a lot of equipment is because of the fact that you're talking about equipment that's being developed in competition with other equipment. So there is by necessity a duplication of effort, something that engineers like me absolutely hate. It's called inefficiency. So because of the fact that you have different companies and you have different organizations developing their own things and not opening the plans, then we can't necessarily improve on each other's work and start to converge towards something that's more sustainable, less costly, and can be made in larger and larger batches to bring the overall manufacturing cost down. Anytime that somebody's making profit off of a research piece of instrumentation, there's usually something wrong with that system. And speaking as somebody who does open source for not-for-profit now with FieldKit. And so by remaining in a closed source space with any of the equipment that you choose, you're enabling that to increase expense. Just my 2 cents on it. And I think that might be a very good focus for us to take, is that anything that's going to be funded insofar as further development of hardware needs to necessarily be open to begin with, so that improvements can be made privately or publicly, even better.
I agree.
I'll get off my soapbox now. Sorry.
Yeah, if I can chime in for a second. I mean, I think that development with the open source model is fantastic. We support that. It does drive innovation at a lower price point than can be commercially viable sometimes, because we have to pay employees, lights, medical insurance, all those kind of things from a private company perspective. But there's also something to be said where you've got a solution that is supported and has consistency in manufacturability and so on, which you don't always get in that open source community standpoint. So I like seeing innovation with open source, and then taking that technology or that concept, because it's opened up by acoustics, especially with the audio moss and so on out there. It made accessibility for bioacoustics at a lower price point that we certainly couldn't reach for a long time. Although I know with that price point of the Micro 2, I think that's changed. But it allowed volume to increase. The more we can sell, the lower the price point of the manufacturing, then the lower we can offer it to the community too. So open source side enables markets. The private sector, I think, takes it to the level where you can have reliable data, that you're not losing 30% of your data, which sometimes happens with open source equipment.
I'm conscious we're right on the half hour. So I want to throw one last question. So forgive me for going a little over. Next week, I'll be back in control of our time, slightly tighter. So we'll have more of a discussion. But this first week was always going to be a bit long. But I wanted to ask all of our speakers to have final comment on what you would like people to, go home. If anyone on this call could go home understanding one key take-home message about bioacoustics hardware, what would you want that to be? Or what is like the #1 development on the horizon that would completely revolutionize what we're doing right now? You pick your own adventure. There are 2 questions you can pick from. And Carlos, do you want to take it first? What's your one take-home message, or what's one development on the horizon that would completely revolutionize what we're doing right now?
Things that I like to see developed. I think I probably have a slightly different context to a lot of people who are in this, because I do a bit of research, but most of my context is professional ecology consultancy, and so I'm interested in open source, but support it, and I don't know, I prefer fairly consistent, decent tools, and luckily, because the contacts I work in, I can afford to pay for those. But I think I'm super keen to see non-specialists use bioacoustics as much as possible. And I think a lot of the work that's been done in the university sector, for example, is, all the cutting edge research. We can do this and we can do that if you've got, 1 billion postdocs working on it. So tools that are easily applicable, easy to use, are really useful. And I think we have the hardware solutions now, whether that's an audio moth or a wildlife acoustics kit in terms of suitable recorders. I'd like to see more easy to use software tools. And so BirdNet, which I use, but is slowly coming out of the command line into GUIs and other solutions like that. I'd like to see those sorts of solutions being able to be used by a nature reserve manager who knows nothing about bioacoustics but can stick a recorder out and analyze that in a simple way to get some information about their site.
Wonderful. Martin, do you want to take it next?
Yes, take-home message. I think from a DAS point of view, or distributed acoustic sensing, we are scratching possibilities and we are exploring them. And if you come up with ideas, where can this be used in my neighborhood or whatever applications, I would love to hear about that. So I hope the take-home message is that I think this will be used for a lot of other applications than listening to waves, for instance. It's a lot of possibilities out there that we haven't really discovered yet.
Amazing. Mona, What's your take-home message?
Yeah, take-home message. Technology continues to advance. I mean, Laurel talked about what we did in 100 years. My presentation kind of focused on what did we do in the last 10 years. So when you think about what's coming down the pipe, you know, my background's actually in electrical engineering, and the amount of iteration and advancement that get done in the span of 3 to 7 years is amazing. So for those of us that want that solution now, I would just say be patient, because the technology is going to get there in the next, you know, 2 to 5 years on a massive scale that we can leverage. So it's coming. So yeah, that's my message.
Laurel, do you want to take it home?
And I think that Carlos's point about having it accessible to non-specialists, you know, if we imagine a future where people can pull data from lots of places for big scale insights, we have to be able to get to the point that we can be doing on-device processing. Anytime I'm talking about people about, you know, LED certified buildings or things like that, and you get to the step that, okay, now you go out and you get your SD card and you download your files and you rename them and compress them. It's just, and people glaze over. So getting to the point that you can get pre-processed data that can be fed into a system that what you're seeing is maps and detailed analytics. You know, the researchers are always going to want what's under the hood, but for broad audiences, being able to put out a device and see a visual portal that's telling you something about the biodiversity, I think will be really important.
Couldn't agree more. We're going to wrap up there. Thank you everyone for joining us for the first virtual meetup in this series. We look forward to seeing you back here next week, same time, and for the following weeks after that, as we delve further into the world of bioacoustics and looking at where we could go in the future with this really important tool. So thank you everyone. A big thank you to all our speakers, and particularly our team, Vanessa, who is actually the brains and the heart behind this whole series. So if you want to talk ecoacoustics, reach out to Vanessa, and if you want to find out more about the Horizon Scan and this whole project, she's the one to talk to. Big thank you to Talia and Alex as well, and everyone else. We'll see you next week. Thanks so much. Bye.